A computer with only 1 bit? How is that possible? In this video we will build a simple 1-bit system on a breadboard and find out about its capabilities and how it works. The heart of a 1-bit computer is a 1-bit processor. The MC14500 from Motorola is such a CPU. Introduced in 1977 and made until 1995, the MC14500 was designed for simple industrial control applications. That's why it's called an Industrial Control Unit, or ICU for short. Unlike usual CPUs, which can process up to 64 bits at a time, the ICU can only process one single bit. That's why it's limited to basic logic operations like OR, AND a few more that I will cover later. These are done in the logic unit and controlled by the 4-bit instruction register, giving it 16 commands in total. The results of these then show up in the result register, which here is a simple D latch. As you can see, the contents of the result register are fed back into the logic unit where they are concatenated with the level on the data pin. In this example, the XNOR command is simply an exclusive OR whose output is inverted. This means that the output is 1 if both inputs are equal and 0 if they are different. So we can use the XNOR command to toggle the contents of the result register. But now let's wire up the ICU on a breadboard and see how this happens on the real thing. I start with the 5V power and ground connections. Next are the dip switches, which I use to set the opcodes. And from there I connect the 4 input pins of the instruction register. Now I plug in 4 LEDs which will show the opcodes of the instruction that I have set on the dip switches. Since the ICU is a microprocessor, it needs to be clocked. For this purpose it has an internal RC oscillator whose frequency can be set between 10 kHz and 1 MHz by a resistor between 2 of its pins. However, I wanna go through this step by step, so I'm going to clock it with a push button connected to pin 13. A 10K resistor pulls the clock pin to ground when the button is released and connects the pin to 5V when the button is pressed. These buttons bounce like hell, but a 1 microfarad capacitor helps. Now let's take control of the result register. Pin 15 represents its current value, so I connect an LED to it. Now let's go ahead and fire this thing up. I try the XNOR command, which is 0111. You can see that the LED toggles every time I let go of the button. A rising edge moves the instruction to the instruction register, a falling edge starts its execution. Any processor is pretty much useless if it cannot exchange information with the outside world. So I wire the data pin of the ICU to the last of the 8 dip switches and also a green LED that indicates its level. Now I need to bring the value on that 1-bit data bus into the result register so I can perform logic operations on it. For this we first clear the path from the data line to the logic unit by writing the 1 on the data line into the input enable register. This is done by the input enable command 1010 and pressing the clock button to execute it. After that we can issue the load command, which is 0001. And now everything works fine. Each falling edge on the clock pin transfers the value on the data pin to the result register. Now let's try the opposite. I'd like to output the contents of the result register to the data pin. To visualize what's happening, I connect a red LED to the right pin. Then I invoke the output enable command to clear the path to the data pin. Now I enter the store instruction 1000 and also turn off the 5V level I just read in. This gives the ICU control over the green LED. By clicking the button, the 1 in the result register is brought to the data pin and the green LED lights up again. At the same time, the red LED on the right pin indicates that the ICU has just output a value. Notice what? I just executed a program. But is this configuration useful? Well, For being a control system, it needs some memory to store this program. In the manual, Motorola provides an example of a minimal ICU system. The ICU has neither address pins nor a program counter like normal processors have. That's why the memory addresses have to be generated by two daisy-chained 4-bit binary counters which are clocked by the RC oscillator of the ICU. This way we get an 8-bit address that addresses 256 bytes of a PROM. The most significant 4 bits of its output bytes go into the instruction register and select one of the 16 commands. When the system wants to read an input value, the least significant 3 bits determine the input to be routed to the data line. And if the system wants to write an output, the bit selects the output latch to set. If bit 4 is set, we get 8 additional outputs whose values can also be read by the program. You can think of this as an 8-bit RAM. If you want to build this circuit the most easy and durable way, I recommend you to build it on a PCB from PCBWay. Upload your design files to the website and configure the boards online. Their PCBs are of the best quality and highly reliable. That's why PCBWay is my preferred PCB supplier. Soldering is done in no time and it is a real fun. So check it out. Since I didn't have these chips available, I started to build a minimal ICU system with what I had on hand. Here is what I came up with. Instead of the 2 counters and the PROM, I use an Arduino for emulation. There the clock signal of the ICU triggers an interrupt routine that outputs the bytes of an array one after the other on the Arduino's digital pins. Looks somewhat like assembly language, doesn't it? Above I defined the symbols for the hex numbers that make up the actual ICU programs. After the Arduino has output the last element, the program counter variable is reset and the program starts again from the beginning. That means that the ICU programs usually run in an infinite loop. And here's the whole ICU system on a breadboard. As an input selector I have a circuit made of 7400 NAND gates and 7404 inverters, which gives me 2 inputs. As outputs I have 2 7474D latches and another logic that selects one of them according to the I/O address. This gives us 2 inputs and 2 outputs that can be concatenated by software. Now let's write a little program. Output 1 should go high when both input 1 and input 2 are high. And here we go. The IAN and OAN commands enable data input and output of the ICU. Then input 1 is loaded into the result register and ANDed with input 2. Finally, STOQ1 writes the contents of the result register to output 1. Now I want output 2 to go high if only one of the 2 inputs is high. So I load input 1 into the result register again and XNOR it with input 2. STOC then writes the complement of the result to output 2. Remember this? XNOR returns 0 if both inputs are unequal. So we need to invert its result with STOC to get a 1 at the output. This way we can realize any logical concatenation between the inputs and the outputs in software. And the ICU can do more than simple logic. Besides logic operations, it also has a jump and a return command to call a subroutine. But how do these actually work when the processor has no program counter? Well, with the jump and return commands the ICU outputs a short pulse on the corresponding pins. This sets the external program counter circuit to a different start address and loads the instructions from there until it comes to a return command. Then it jumps back to where it came from, but skips the jump so as not to get caught in an infinite loop. To emulate this, I connected the jump and return strobes to 2 input pins of the Arduino and extended the sketch a bit. When the program hits the jump command, the ICU fires the jump signal. The Arduino then starts executing the array with a subroutine. When it comes to the return command, the ICU sends a return pulse and the sketch toggles its execution back to where it came from. The skip on 0 command skips the instruction that follows it if the result register contains a 0. If we put this in front of the jump command, we get a conditional jump. So the jump only happens if there is a 1 in the result register, otherwise it will be skipped. Returning to the main program can also be bound to this condition. And here are the program arrays of the ROM emulation again. When I press the button, the load command writes a 1 to the result register. The store and store complement commands then turn LED 1 on and LED 2 off. As the result register now contains a 1, the skip 0 command does not skip the jump command and the code in the second array is executed. There it polls the value of input 2 and toggles the outputs again. When the other button is pressed, a 1 is written to the result register and skip on 0 gives way to the return command, which brings the system back to the state where it was at the beginning. This is how we've just programmed a state machine. In this case, an RS flip-flop. And even more complex programs can be made if the ICU system has some scratchpad bits like in the example from the manual. But I think that this pretty much shows the concept of a 1-bit computer. If this video gets at least 500 likes and 50 new subscribers, I will build something awesome with the ICU. So don't forget to like and subscribe. Also enable notifications to never miss any of my videos. Thank you for watching. Oh, and of course any support per Patreon or channel membership is highly appreciated. Get ad-free preview videos and other goodies, so check it out.